We were talking about the problems that huge amounts of data that IoT systems generate can cause. And the idea is that if you have large amounts of data, it quickly becomes infeasible for you to use a standalone PC or something like that to process all that. Imagine if you have say 10,000 or 20,000 nodes in the field and all of them are sending data continuously. Very quickly, no matter how powerful your PC is, it's going to get overwhelmed. So a single standalone machine cannot handle all of that, and because the data is so large, it will not fit into your normal RAM also. If it doesn't fit into your normal RAM, or if it doesn't fit into your normal hard disk, you're going to have problems. So how you are going to deal with this is by looking at a different kind of approach to handling large amounts of data. And what we do is we look at the typical Hadoop system, which is used in the traditional IT industry itself for processing large amounts of data. So whatever is already implemented in the field of conventional IT when they deal with big data, big amount of data, same thing can be used for IoT systems also, because more or less the requirements are the same. So like typically the large amount of data that come for typical IT systems are from things like banking transactions, or from uh, things like, say, if you have a very large store or something, say Walmart, or maybe even if you take the example of online stores like Flipkart or Amazon, they generate huge amounts of data which need continuous processing to get better customer insights, to decide which things to put on offer, how the sales are doing, and so on and so forth. And that cannot be done using standalone systems, so they have to go for something like a distributed computing system which can leverage multiple systems at the same time and do things parallelly. That is where Hadoop comes in. And as you can see, the initial impetus for this was projects at Google and Yahoo, where they wanted to kind of give web search results as quickly as possible. Right. So now what I will do is, I'll just give me a second. I will share the screen, and I'll give you a very small overview of what is Hadoop. Okay. Um, just give me a second. Yes, can you see it now? Hadoop
Yes, sir.
summary slide. Can you see it? Yeah. And just let me know if the audio is available. If it is not, please let me know.
Let's rewind to the days before the world turned digital. Back then, minuscule amounts of
Yes, sir,
data
we
were
can hear.
at a relatively sluggish pace. All the data was mostly documents, and in the form of rows and columns. Storing or processing this data wasn't much trouble, as a single storage unit and processor combination would do the job. But as years passed by, the internet took the world by storm, giving rise to tons of data, generated in a multitude of forms and formats every microsecond. Semi-structured and unstructured data was available now in the form of emails, images, audio, and video, to name a few. All this data became collectively known as big data. Although fascinating, it became nearly impossible to handle this big data, and a storage unit processor combination was obviously not enough. So, what was the solution? Multiple storage units and processors were undoubtedly the need of the hour. This concept was incorporated in the framework of Hadoop that could store and process vast amounts of any data efficiently using a cluster of commodity hardware. Hadoop consisted of three components that were specifically designed to work on big data. In order to capitalize on data, the first step is storing it. The first component of Hadoop is its storage unit, the Hadoop Distributed File System, or HDFS. Storing massive data on one computer is unfeasible. Hence, data is distributed amongst many computers and stored in blocks. So, if you have 600 megabytes of data to be stored, HDFS splits the data into multiple blocks of data that are then stored on several data nodes in the cluster. 128 megabytes is the default size of each block. Hence, 600 megabytes will be split into four blocks, A, B, C, and D of 128 megabytes each, and the remaining 88 megabytes in the last block, E. So, now you might be wondering, what if one data node crashes? Do we lose that specific piece of data? Well, no. That's the beauty of HDFS. HDFS makes copies of the data and stores it across multiple systems. For example, when block A is created, it is replicated with a replication factor of 3 and stored on different data nodes. This is termed the replication method. By doing so, data is not lost at any cost, even if one data node crashes, making HDFS fault tolerant. After storing the data successfully, it needs to be processed. This is where the second component of Hadoop, MapReduce, comes into play. In the traditional data processing method, entire data would be processed on a single machine having a single processor. This consumed time and was inefficient, especially when processing large volumes of a variety of data. To overcome this, MapReduce splits data into parts and processes each of them separately on different data nodes. The individual results are then aggregated to give the final output. Let's try to count the number of occurrences of words taking this example. First, the input is split into 5 separate parts based on full stops. The next step is the mapper phase, where the occurrence of each word is counted and allocated a number. After that, depending on the words, similar words are shuffled, sorted, and grouped. Following which, in the reducer phase, all the grouped words are given a count. Finally, the output is displayed by aggregating the results. All this is done by writing a simple program. Similarly, MapReduce processes each part of big data individually, and then sums the result at the end. This improves load balancing and saves a considerable amount of time. Now that we have our MapReduce job ready, it is time for us to run it on the Hadoop cluster. This is done with the help of a set of resources, such as RAM, network bandwidth, and CPU. Multiple jobs are run on Hadoop simultaneously, and each of them needs some resources to complete the task successfully. To efficiently manage these resources, we have the third component of Hadoop, which is Yarn. Yet another resource negotiator, or Yarn, consists of a resource manager, node manager, application master, and containers. The resource manager assigns resources. Node managers handle the nodes and monitor the resource usage in the node. The containers hold a collection of physical resources. Suppose we want to process the MapReduce job we had created. First, the application master requests the container from the node manager. Once the node manager gets the resources, it sends them to the resource manager. This way, Yarn processes job requests and manages cluster resources in Hadoop. In addition to these components, Hadoop also has various big data tools and frameworks dedicated to managing, processing, and analyzing data. The Hadoop ecosystem comprises several other components like Hive, Pig, Apache Spark, Flume, and Scoop, to name a few. The Hadoop ecosystem works together on big data management. So, here's a question for you. What is the advantage of the
Okay. I think right. So I think that was a video that you could understand. Just one second. Okay. Right. Okay. Was that video any useful? Like I hope you are able to kind of get.
Yes,
Hello.
yes, sir. We understand.
No. Did you kind of were you able to watch the video completely until the point where I stopped?
Yes, sir.
Yes. Yes. The connection is a little weak here, so I'm kind of not able to hear you people properly. But anyway, so what you have seen in that video is an overview of the entire Hadoop system. So we will just look at that in a little bit detail in today's class and hopefully finish it off quickly. And if you are interested in working with big data and so you have very good implementations in Python, which will help you do this, or you can also do big data processing using MATLAB. I usually use all my big data analytics is done via MATLAB, mainly because I kind of find that a lot more easier to work with. I do not have to do any setting up or any other extra stuff. I can use the computing cluster that is available with us here in the campus and it's not very complicated to set up also. So you have several implementations that are available. You can do this in Java, you can do it in Python. You can also implement it using, and you can set it up using very easily using MATLAB also. So I usually use MATLAB, but Python also is very popular. So that is one thing. And some of the major features that uh, were already discussed in the video, but I would like to kind of share it with you again. The idea is that the Hadoop ecosystem is, or the Hadoop framework is extremely reliable. You have a multiplication factor of 3 by default, which basically means that every data that you have given, say for example, you give it a chunk of data, like for example, you give it about 500 GB of images, which you want to classify for something. So each of those 500 GB of images is cut into small blocks. That means some images, all images are grouped into different small chunks, and then each chunk is kind of replicated by a factor of 3, which basically means that you will have 3 times the amount of data, at least at the initial stage, so that during the initial processing at least the data is not lost completely, even if some nodes kind of fail or something like that. So that is kind of tied very closely to the point number 6 that you see here, fault tolerance. Reliability and fault tolerance are kind of very close to each other, and that's why we say that the system is very close. Unfortunately, the price that you pay for fault tolerance is that you have to have a little bit more amount of space to store it. Now that we have got a lot more cloud computing facilities, you have no major issues with this, because you can it's become very easy to set up a Hadoop cluster. All those things kind of go in the background. You just have to push your job, and all this stuff kind of gets automatically done at the back end. Only when you're setting it from scratch in your own organization, you may need to know all the details of Hadoop and the process. But other than that, a lot of this, if you're doing it in the cloud, is taken care of by the cloud service providers themselves. You just have to give the location of the data and what do you want to do with it, and automatically kind of it gets pulled into the cloud and the work happens. But it's good to know what is happening inside. So that is the idea, and you have the system which is also scalable. Why do you call it scalable? You call it scalable because this is a distributed file system, which means that as new data comes in, you can request for more resources, which basically means that you will have more number of elements or more number of processing units getting added into your cluster. And because you have the ability to split the work into small chunks, you can add smaller units rather than kind of spending huge amounts of money and refurbishing the whole system and making it totally new. So it's like adding newer and newer blocks into the system. It's just like having building blocks or Lego blocks for your processing unit. So if you need more, if you need to make a bigger system, you just add more blocks into it, and the blocks will by themselves be very small. So that is the idea behind scalability at a reasonable cost for Hadoop systems. And then obviously there is something that runs in the background which does something called load balancing, which ensures that all the nodes are working to their optimal extent. Otherwise, some nodes may get full overloaded, other nodes may get underloaded. So the performance is managed dynamically, and so that all the nodes kind of receive equal weightage based on the processing power available and the RAM available at each node. So that kind of happens automatically at the back end for now, for most of the systems now. Okay, and the third reason that we have is economical. This is what we already discussed. It's like adding building blocks. Individual building block will be small. You could be adding your small laptop also as a part of a node. You could be adding a Raspberry Pi as another node. Actually, you can set up a Hadoop cluster just using Raspberry Pis. I have seen a parallel computing cluster which uses up to 128 Raspberry Pis as a parallel kind of a cluster supercomputer. You can set up that using Hadoop, and it will not be a very difficult thing to do. So you could have multiple different devices which could be forming nodes in a Hadoop ecosystem, or a Hadoop system, file system, which will take all these things. And obviously there is distributed processing, which is a key function of Hadoop. And storage is also distributed because you cut the data into small chunks, and that kind of gets stored in as individual units. So this data may be lying on one hard disk, or it could be from multiple hard disks. The data could be sourced, but in the Hadoop uh, HDFS system, which we'll be seeing next, uh, it does not matter where the data is physically located, because the data that you have in small chunks, that each of them are assigned numbers, and whenever required only they are pulled from the hard disk. So you do not need to put all the data into the RAM to process. This is totally different from what you may have done in your machine learning course, right? If you remember in the machine learning course that you did, you must be loading the data into your RAM before you start, right? Was it done like that, or did you pull it directly from the server or somewhere else?
Sir, we did both ways, sir.
Okay, so how was the kind of pulling from, like, did you use data stores or something? How did you get the data from the?
Sir,
How
some
did you use?
databases were hosted on GitHub, sir. We directly imported from there.
No, I mean, like, it was imported into the system, right? It came to your RAM, no, before you started processing.
Yes, sir. Yes, sir.
That's what I mean. I mean, like, I wanted to know if the data is coming into the RAM, because once you load it into the RAM, then the whole data is in the RAM. You are not putting it into chunks and then taking parts of the data set, no, individually. The whole data set was kind of imported from Git into your RAM at one shot.
Yes, sir. Yes,
That's
sir.
what. So that is the difference. I mean, like, if you are using something like in MATLAB, you have the concept of something called data store. So in that way, what you will do is you will only pull small chunks of data from your hard disk or from your cloud container that you have, as and when the need is there. Because if you have like 1 TB of data which you want to process, you cannot load all of that into your RAM, right? Because you don't have that much amount of RAM with you, or 500 GB of data. If you move all of that into RAM, it's not going to work. So that is where all this data store and your Hadoop system comes into picture. You load the data as and when necessary, or split the data into smaller parts, process them independently, aggregate them together, and bring it back to us. So that is where this also Hadoop also works. Storage is distributed, processing is also distributed. So none of the systems get overloaded. You do not necessarily have to use just 1 second. Just give me a second. I'm sorry for the inconvenience. Okay, can you see the presentation now? I've continued to
Yes,
share
sir.
it. Yes. Yeah. So you can see this is the basic Hadoop structure. Just visualizing the whole thing. So you have the work which you push into the master, and the master will take care of that from the there onwards. So you do not have to specify exactly what part of the job is going to which slave. So you do not have that level of granularity visible to you. You may do that if you are kind of managing the whole system or something like that, but this is all done dynamically, right? So your work only is up to this user, and you will push the work back into the master, and that is where your whole control of the system ends. The because of the load balancing and the type of data splitting that happens, all the individual slave nodes that the Hadoop system has, the system will automatically decide who should get what and what chunk you should be getting, and all the processing system and the reverse. I mean, like once the processing is done, the collection and the integration of the results and pushing it back to you will all be done by the system. You do not have much control over it. Your job will typically end at pushing the system or the work into the master. So that's how the whole process will work. Okay. And if, as the video said, you have three parts to the Hadoop system. You have the HDFS, you have the map reduce, and you have the yarn component. So first is the storage. So we will look at the storage system. If you see, this is how the typical system works. You have another graphic. So you have each of the blocks, like the data, huge data that you have. It's basically saying 100 terabytes. It could be more, it could be small, but typically it is of the size of hundreds of gigabytes or more, at least tens of gigabytes or more, right? And you have by default the size of the uh, chunks that you split the data into will be about 128 bytes, 128 MB. So all this 128 MB, multiple chunks are sent to the slaves, and they do all the processing. Please remember that you could have a situation where multiple chunks are sent to one particular slave, or the amount of block sizes these are kind of modified from 128 MB to a larger value so that it can fit the available resources, right? So if you see here in the figure itself, it kind of gives you that idea that you could have multiple blocks which are sitting in the same slave, right? And obviously the load balancing is very, very important. You have to make sure that the job queues are not very large, and that the systems or the slaves are able to process and return the data within a reasonable amount of time. Only when all the data is available back, you can integrate the whole thing together. So that is why you have to do the load balancing becomes so critical, and it all almost automatically always happens dynamically. So you do not have to do much about it. A lot of algorithmic development has gone into the back end of that. So no big deal there. Okay, so this is what is happening as part of the HDFS system. And you can see the master is typically a high-end machine. So it will be like a server class system. And the slaves could be anything which is small. As I said, it could be a Raspberry Pi 4, it could be your laptop, it could be any other desktop system or whatever you have. You could have several systems of different types connected together. There is no requirement that all of them should be of the same type or of the same processing capability. Only thing is that they should be capable of running as Hadoop slaves, and that the Hadoop environment is set up in all of them. All right. So can we go to the next slide?
Yes, sir.
So now we talk about something called the HDFS daemons. It's called daemons, not demons, daemons. So basically what is daemon is typically it's a program that runs as a background process, not something that you directly control yourself. So you have two daemons which HDFS executes in the backend. It's called a name node and the data node. So name node is something that runs on the master machine, that is the front end machine, and it's kind of something which does all the work of monitoring, managing, load balancing. All those things for the data nodes are controlled by that. Data nodes are the slave programs, right? So you have two programs, as we saw in the figure itself. There are two types of systems in the HDFS system. One is the master or multiple masters if you want redundancy, and then you have the slaves. So the program which runs on the master is called the name node, and the program which runs on the slaves is called the data node. Right. So all the system management of the slaves is done by the name node daemon. So it keeps track of everything, which data chunk has gone where, what is the block size that I am using, what is the sizes that I am using, what kind of read write permissions I have, what should be the queue size that is acceptable. All those things are kind of controlled by name node daemon. And therefore, because it does so many things, and so much, it has to do so much of dynamic balancing and changing, and basically the editing the size of the nodes, which nodes are currently being processed, which have already been processed, how do you integrate the data. All those heavy lifting is typically done by the name node daemon, and that is why it typically runs on a system which is usually a kind of, is typically the most powerful of the lot in the HDFS system. So you usually have very good or basically server class system which runs these things. Okay, so that is one major thing that you should know. And the program which does all this controlling is typically referred to as the name node daemon. Not daemon. And obviously the second part of that is the data node which runs on the slaves. So the data node daemon runs on the slaves, and it is the one which actually does the processing on the slave nodes. So it adds, removes, replicates all kind of small blocks that are coming in. All that basically is done by the data node system. Please remember, we are not looking at the processing part yet. We are looking at only the management of memory. Okay, HDFS is only concerned about management of memory and moving the data to and from the master to the slaves. Okay, so master slave data movement and storage is the only work that HDFS does. The processing and other stuff is done by the systems that we are going to talk about next. Okay, so that's basically it. And you can see by default the HDFS gets the report from the individual data nodes at every 3 seconds, and you will get the state of health of the system also, like how much load the CPU is running, usually the temperature of the nodes. So everything kind of basically comes back roughly every 3 seconds. You can change the frequency of that also. So it will be just like a small ping which comes in with all the information. So that is what happens as far as the storage is concerned. Okay, storage and data transfer. So once the storage and data transfer is typically done using the HDFS system, we also saw this replication factor, so I'll not go into this in great detail. So if you look at this, you have the read-write process completely taken care of by the HDFS system. And once that is done, you go into the next layer where you do the data processing. And that is typically done with the help of something called map reduce. We saw that in the video also. It basically requires you to map the individual parts of the data into some kind of a code which is much smaller in size, and which results in a reduction of the overall size of the data. You can recreate the data by looking at that. So it's basically like compressing of data, but not actual compression. You're basically reducing the size of the data by using something called the key value pairs. Right. So here you have this graphic which will help you understand. Okay. So in this you have the data. There are two phases. One is the map phase and the reduce phase. So once the mapping basically converts the data into a key value pairs, which basically means that you assign, if it's a text data, for an example that we saw in the video, you could create a data dictionary with numbers being assigned to each of the words. And if you just put it in a sequence of numbers, you will be able to recreate what the words are. So you can basically reduce the size of the whole overall kind of data set by a very large amount if you do this. Okay, so like for example, you may have very long word which could be replaced by one single number. A 2-digit number could be kind of representing that huge text or a huge string. For example, the same map reduce, this one word could be represented by something like, say, a number called 10. So that coding and all that is typically done, tokenization and coding, etc., is done at the back end. Now you have a lot of built-in functions in both MATLAB as well as in Python and Java to do this for you. You do not have to manually sit around looking at individual components of a data and then try to map it and reduce it. The map reduce typically comes in as built-in functions in both Python and in MATLAB and in Java. So it becomes a lot more easier for you to work with it. Okay. So this is how typically MapReduce will work. What should be the input? So input is typically in the form of a data store that is coming in, which is like in the hard disk or wherever it is located. You just point it to where the data is lying. So it picks up data in the form of chunks, and the individual chunks you will find the key value pairs from that. So each of the keywords are picked up, each of the individual words are picked up, a dictionary is created, and each of them is assigned a value. So once that is done, then you have integration of all of them, because there could be repeated string sets of data which are coming in. So all of them are integrated into one single chunk, and there are markers which are put which will tell you where this data has to be replicated again. So it's like having a small dictionary of words, and with a large sheet where you know which place to put what word in. So when you want to recreate the whole system, you just know exactly which word to pick and place where. So in that way, the whole system becomes much smaller in size. So you have a smaller area where the keywords are stored, and then you have uh, the kind of larger map which you can just basically map the keywords onto. So that kind of reduces the overall size of your data set by a very, very large amount. And this works very, very well. So if you want to look at the map reduce function, I will suggest that you go to the help of MATLAB. I hope you know that we have university license for MATLAB, right? Are you aware of this?
Yeah, yes, sir. We installed it last semester.
Yes. Now you have the MATLAB 2021 B version is available now. So a lot of improvements have happened in that big data analytics part also. So please have a look at that. You will find a lot of stuff in that. I'll just show you. Let me just. You want to just check in the internet itself. You will find that this is what you will see. I'm not seeing it here. Yes, so if you want to just check on the help of MATLAB, just go to MathWorks and just look at MapReduce. You will find the complete details on how to use MapReduce, and you can see what are the algorithms that are available, what is the process. There's a good amount of tutorial which is available for this. The whole step-by-step process on how to deal with MapReduce and how to build effective algorithms using MapReduce, all that is given to you. So these are sample examples which you can use. Okay. So if you have a very large amount of data, how do you deal with this? Is something you can have a look at it. So you can see here, this is something which you can which you will most likely connect with a lot easier, I think. Logistic regression is something that you may have already done. I think it was a part of your machine learning course, right?
Yes,
Did
sir.
you do this? Yeah. So you can actually use kind of fit logistic regression models even for data which do not typically fit in your memory. Whenever you did the logistic regression problem, which was the data set you used for logistic regression? If you remember, can you just tell me? If you remember, I don't know. Okay. Anyway, I don't expect that, but the data set that is given in this example for in MATLAB is the one which typically will not fit into a typical RAM. They have taken a smaller subset, that's why it is called airline data small, but the actual airlines data is kind of quite large. That will usually not fit into your small RAM systems, right? So that's an example that they are showing on how it can be used for applications which typically require a lot more RAM than it's available with normal users. That is the idea of MapReduce. You will reduce the size of the data and you basically map it into something called key value pairs. And the third layer that you have is the yarn, or yet another resource negotiator. Okay, so this basically is to improve the idea of MapReduce. Okay, and what does MapReduce do? MapReduce basically has three components. It manages resources, nodes, and how to use the jobs. So you can see the resource manager in Yarn, because it's a resource manager, it will obviously be running on the master node, because this is the one which basically controls all the processes. So you remember we had HDFS system, part of it was running on the master part. So you have this Yarn resource manager also running on the master system. So there you are basically controlling all the things here. So basically you control how much RAM should be given, what should be there. So all those kind of things, which are what kind of processing power should be given, all those things are typically controlled by the resource scheduler. Okay. And also this will keep track of the heartbeats from the node manager. If the nodes are working properly or not, that also is taken care of by this particular thing. So you're scheduling the resources, you are controlling, you are just finding out if the nodes are working properly or not. All the event handlers typically run here. So if there are some kind of errors or exceptions happen, all those are typically controlled by the resource manager. Okay. And the second one is the node manager. This also runs on the slave machine. So resource manager runs on the master, this runs on the slave. So just like if you remember name node and data node, so same thing happens here also. So for each individual node, you have an individual manager also. So each individual node manager typically controls the containers which contain all the data. So the containers are typically the ones which contain all the individual processing events that are happening inside, and this node manager typically controls that. And this is the kind of program or the code which sends the heartbeats to the resource manager. If you remember, we talked only about that the heartbeats are sent at an interval of 3 seconds, but what sends that 3-second interval, that kind of ping, is the node manager program. Remember, these are all programs. Okay. And the third case is what you have as the job submitter. Your job submitter typically submits. You can see here the job submitter sends the data to the resource manager, the job to the resource manager. This schedules the resources, and then the processing also happens individually using application master, etc. So job submitter will both transfer and receive the jobs from the resource manager. Okay, and the containers typically will be running the applications, and once the data is when the processing is completed, the job will be sent back, and from there onwards it goes back into the main system where the integration of data will happen. So that is the idea of yarn. And we quickly go to, how much time do I have? I have like 7 minutes to go. So quickly I'll just wind up this thing. So this is the overall Hadoop ecosystem. Why I am going this in complete theory is mainly because you do not have to basically learn this in theory, in practice. But if you are interested, maybe I will just upload a couple of videos on how to use MapReduce for these kind of large data sets which are coming in. I have a data set which we have worked with before, so I'll try to share that with you and maybe put a YouTube video on how to use that, especially in MATLAB. How that can be done very easily. In Python, it can be a little code intensive and maybe difficult for people who are not very used to this. But MATLAB should be a very easy thing to work with if you are kind of doing this. But again, MATLAB will kind of what you may say, take away a lot of complexity that is involved in this. So you may not be able to know individually what each of these things are doing. For that, Python is a better solution. But it takes but big data is a course in itself in many places. I think even in the computer science department, big data by itself is a course, a 3-credit course in itself. So I do not think we have enough time or resources to complete this in 1 week or so. That's why I'm just going to give you some introduction, and hopefully maybe I'll just upload one example in YouTube. I'll not be asking you anything on this, the practical implementation aspects of this in the end semester also. I just want you to be aware that these things are existing. This is how you do the processing also. So that's the idea, and you can see here that the whole ecosystem has got multiple things in it. So you have multiple ways in which you can, these are the 3 basic things that you're seeing are the MapReduce, yarn, and the HDFS system. And along with that, you have multiple add-ons which will help you understand the uh, data, make sense of the data. So you have things like Mahout and Drill, which help you do machine learning and analysis of data. Scripting is typically done by Pig and Hive. And then you have things like Scoop and Flume that kind of help you with the data collection and cleaning and all those kind of data kind of things that can be done. I have not worked with Uzi, so I don't know what that is in great detail. But mainly you will find that most of the big data people will typically be working with uh, Pig, Hive, and Mahout. So that is something that you have to, it will be helpful if you are able to understand what those things are. But anyway, it will take a long time for us to work with. So I just want you to remember that at least the terminology, what it is about. Okay. And now very quickly, we look at the idea of big data and the edge analytics. So here what you have is when you talk about big data, you are looking at processing data at a central location. In edge computing, you are talking about processing data locally, mostly. So typically both of them now work in sync with each other, because even after doing a lot of edge analytics, the data that is getting created is extremely large. So that is where the whole problem is coming up now. You need to have both right now. You need to use the edge computing to filter out all the unnecessary data, and the big data analytics is required to process all the data which is relevant to make sense of it, right? And then you have the idea of streaming data analytics, where you do not have the luxury of having data which is stationary and stored somewhere. That is another problem, which basically means that you need to analyze the data on the fly, because the trends are changing, data is changing. So all those things require you to do processing in a real-time basis. So if you are really interested in doing something on streaming data processing, I will suggest that you just, one simple example is that you could look at the the tsunami warning data set that, not data set, tsunami warning association that they have. There's something called Argos. It's like a set of buoys that exist, that have been kind of laid across the Indian Ocean after the tsunami, Indonesian tsunami that kind of happened. I hope some of you may be remembering that there was a huge devastating tsunami about decade ago or so, and it was kind of very damaging to a lot of countries. So after that, tsunami warning system has been laid out in the Indian Ocean, and uh, there are something called buoys, BUOYS, so which are basically kind of floating sensor nodes which are in the ocean, and they're continuously sending data into the cloud, and that data is available for you to process, and you can kind of get trends or maybe generate warnings if there is any kind of tsunami that is likely to come. So that is one clear use case example of where big data and streaming analytics can come in handy. But obviously the data is not freely available. You'll have to get permission from them to use that data. But if you're interested, maybe you could look at that. It's called the Argos project. So that is one example where this kind of real-time streaming analytics will be useful. Each of those buoys which are floating around in the ocean are examples of IoT nodes. So the idea, and you can see that we can do it on the. This is something that we have already discussed. So can be done on the cloud or can be done on the individual areas. So typically the edge streaming analytics, if you want to perform, if you want to do it on the location itself. So for example, if you want to make the buoys at the Indian Ocean more intelligent, you have to kind of capable, or kind of make them capable of handling that processing power. And the advantages that you will get as a result obviously will be that the amount of data that is generated will be reduced, because only the relevant information will go, not all the information that is going on. So obviously your bandwidth requirements will reduce, and if there is a possibility of taking any action at that location itself, that also is possible. So if you have smart devices, they can automatically recalibrate themselves, or they can automatically readjust according to any failures or any drift in the measurement. Right, so you now have smart devices even in the industry which can do auto calibration. I don't know how many of them, like, have you heard of something called the drift in measurements? Measurement drift, like if you have worked with sensors or something, have you heard of something called sensor drift? No.
Sir, is it like from a calibrated value, the measurements getting drifted, will be drifted as the time passes? Is it like that?
Yes, exactly the same thing. So like for example, when the system was new, it would be giving you some kind of values, but as time progresses, you will see that if you have a weighing machine, initially it was giving, when nothing was put on it, it will become 0. But over a period of time, you will see that it has changed, it's become worse, and even when you don't put something, it shows 0.01 kg or something. Or maybe sometimes when you put the weight on it, that you know is 5 kilos, it will show 5.01 or 5.02. You put 10 kg weight on it, it will show you 10.02 or something like that. So there kind of is a measurement drift that is happening. So typically what happens in this case is that once you see that, okay, this problem is there, you dismantle the whole system, you recalibrate the whole system, reprogram it, so that the system is now again back to correct. So either you replace the sensor or you recalibrate the system so that 10.02, automatically you add minus 0.02 to all of those, so that it kind of comes back to the normal readings or the correct readings. So this is typically done manually in older systems. But if you have a smart device or a smart system, it is capable of recalibrating itself. It will automatically be able to sense that, okay, my readings are off by this much. So there are self calibration modes available. So once you put it in the recalibration mode, the system will automatically learn by itself, and it will recalibrate itself to make it correct. So some help externally will be needed, and you will have to change the mode to recalibrate so that it automatically calibrates itself again. So auto self recalibration is something that you see in smart devices, very popular in the industry now, because in industries where you have the device which is kept for 20, 30, 40 years and not touched or difficult for people to reach, if you have self recalibration or auto recalibration built into the device, nothing like it. You do not need periodic recalibration. You don't want somebody to go into the field, maybe in the cement plant or in chemical plants where there's a lot of chemicals around and somebody endangering their health, to go there and recalibrate the system and come in. So the system can do it by itself, well and good. So that is where a lot of the edge computing comes in handy. Okay. So we'll go into the edge analytics core functions in the next class. I think we are already out of time. So I will stop with this for now. We will very quickly finish this in the next class. And I am planning to conduct at least 1 or 2 quizzes before the end of this semester. Okay, so you have, I will be giving you one more presentation on this. After that, we would have mostly wound up the whole thing. I think the classes will be there only till next week. The week after that, you have the exam, right? Exams are
Yes,
beginning
sir,
on
from 21st, 22nd, sir.
Yes. Yes, yes. So most likely I will finish it off before that. And in the next discussion hour also, I will take the regular class only. Okay, so I think the discussion hour is on Thursday. Yeah, so in the Thursday's discussion hour also, I will be taking regular class so that we can wind it up quickly. I do not want to extend it to the last class, last day's last class. Hopefully we'll finish it off earlier than that. And then there may be 1 or 2 small quizzes to cover the whole portions. All right. So that should be it. I'll just download the attendance. Just give me a second.
Sir, a request from our side, sir.
Yes.
Sir, since this week is going to be the final week for everything, we have a lot of work this week, sir. Every day we are spending around 7 to 8 hours other than the class, sir. So can we have the assignment date from 13th to 17th, sir? You actually give a lot of time to do, but this week is very tight for us, sir. That's why we are asking.
But then how will I, because I have to read every assignment, no? So how will I kind of release the internals before the exams end? Like before the exams, you have to give the internals, no? Is it okay if
Sir,
I kind of delay that also?
Sir, that I don't know, sir. But even if it's on Saturday itself, we are having around many of the class members are having seminars to do, and we still didn't have any CN waivers, sir. It started this week only, sir. That we have to do, and we have a lot of work, sir. We are already very pretty tight with our work. Just a 1 or 2 days is enough, sir. Really.
No, it's okay. I mean, like if I give you time till 17th, the problem is that I will start kind of evaluating that assignment on 18th, and it will take at least 3-4 days because I have to read the whole thing, no? So it will take me at least 2 to 3 days to complete the whole thing. So I'll be able to I will not be able to release the internals before the exam. I hope it is okay for you people.
Yes, sir. It's okay, sir.
Okay, then.
Last semester, many subjects it was released after our end semester exams. I think it's not an issue.
Okay, if you people have no problems with that, then I don't have any issue. So when will you like the date to be?
It can be on any day, sir. After, but not on this week. Like it can be on after 17th or 17th. Sir. Many people
Okay,
are asking for 17th. Since Viva everything will get over and we can get time to focus on the assignment.
then do one thing. I mean, like as a representative, just can you send an email to me, putting a date? Just decide on a proper date and just tell me that this is the date we will like to submit.
Sir,
I could not hear you. Still nothing, Kishore. Your voice is very robotic. I can't hear anything. No.
Sir, I think Kishore is saying that it's fine and we'll send an email.
Okay, he's saying that he can
No,
send
sir,
an
no.
email.
No, sir. 17th is okay, sir. I said 17th is okay, sir.
No, just send an email. I think that will be okay. Then I can kind of change it in AUMS here.
Okay, sir. I'll send.
That should be fine. Because it has to be, because otherwise they will ask me from the department, why did you not release it, and so on and so forth. So I can at least
Yes, sir.
show
Thank you,
them
sir.
that
Thank you.
you people kind of have a lot of work to do. No, I understand that. I mean, like it's very intensive, and uh, like even for the midterm exam, I think the Viva slots were not mentioned in the exam slots also.
Yes, sir.
So it's kind of after the hours only you are doing this. I understand that. So just send a mail. I'll just change the dates accordingly. Okay, no
Okay,
worries
sir.
there.
Okay, sir.
And you are doing it as a pair assignment, no? So that also should
Yes, sir.
reduce
Yes, sir.
some. Okay, then no issues. Just send me a mail. I'll change the dates. No issues.
Okay, sir.
Okay. Okay then. Thank
Sir,
you all for.
I had a quick
Yeah.
question.
Go ahead.
Like Amrita has like this compute cluster. Is it like open to use by students?
You can go through faculty. It's available for faculty right now. So if you can give the job to faculty, they will push it from their side.
Okay.
Because the
So,
logins are given only to faculty right now.
right.
So you can like if you ask the faculty, they can like and if you point out the location to the of the data to the faculty, they can run the job from their side.
And can this be like any TensorFlow training model, or does it have to be something specific? Like, are there documents that I can read on this?
I don't remember exactly. You can do anything, and basically, I have seen people running ANSYS on it. COMSOL is kind of being run on that. Uh, they are using TensorFlow. Yeah, anything. MATLAB, you can do anything. But I don't remember where the compute cluster information is available. Maybe with the ICTS only. You have to check out. But since it's only open to faculty now, so you will have to go through them.
Okay, sir.
Okay, so what is your problem is in which, I mean, like, is it going to be TensorFlow or?
Sir, I mean, there have been times before where, like, 2 times I can remember is like one was during the Amazon ML challenge where we didn't really have the computing power to run our model. And after that, we are also working on a paper. And if we had a bit more computing power, things would go like training would happen faster. So I was just wondering about like wondering if this was an option.
But the thing is, directly students cannot access this.
Right. Yes, sir.
Did you check out the AWS? There is a student account that you can get with some amount of compute.
Yes, sir. So, like, the problem is, um, like, it's limited. And if we go through AWS Educate, we get $100 of credits.
Correct.
But I don't think we get GPU access. And even if we do, it's like very limited hours. Like, last time we checked, I don't think it was feasible for us to use it.
Yeah, that is a problem. So then I think we'll have to stick to the compute cluster only. Better thing will be to just look at the faculty with whom you are kind of trying to write the paper. They can push it from their side.
Yes, sir.
That will be a better option. And anyway, I'm also trying to get something done. Like if AWS kind of computability is kind of also made available, that will be really nice. At least some licenses, if it's kind of available, maybe. I'll talk to ICTS people on this. Let's see. Okay, so yeah, anything else?
No, sir.
Okay, then I think we are done for today's class. Thank you all for attending. We'll continue tomorrow. First, yes. Okay. Thank you all.
Thank you, sir.